Well, here we go. Looks like I just called into jury duty today. So you guys get the one thing that's worse than listening to Mr. Throne talk. Listening to Mr. Throne talk through a video. But here we go. I'm just gonna do this stuff with you and we're just gonna jump right in. Buckle up, get a hold of your materials. You're gonna need your notes. You're gonna need your periodic table. You're gonna need a calculator and you need something to write with. So dig those things out, and as you're getting ready and getting that stuff going, what we're gonna do is, I'll just kind of preview with you, we're gonna go through one problem and kind of all the steps into it. I'm going to try to preemptively show you what usually goes wrong. We've went through one of these before, but we haven't done enough practice to totally feel comfortable with this material. So today's a day where you just get a little bit extra practice in that regard, and hopefully you can do some of these on your own when we're done with this little lesson, okay? So I've got some good news and bad news for you. Let me give you the bad news first. The bad news is we're gonna be working with gas stoichiometry today. Hey, what's the good news? Oh, the good news is there's tons of it. Yeah, I had to tell a dad joke, even to a computer. All right, here we go. Make sure you find this problem right here. Now, it's the last one. If you look in your notes, the last one that deals with gases before we jump into a totally new topic. I know we've skipped some other ones. There's one before it that looks very similar. It's the same reaction, but it says at STP. I don't want to do that one. I want to do one that has more issues that we have to deal with. Okay, so find this one. Starts with C2H6 plus oxygen gas, and it says this is happening at 35 degrees Celsius. So I just want to make sure we're doing one that has a lot of the issues that might arise. I'm just going to do this right along with you. I haven't rehearsed this. I'm going to grab my calculator, and we're just going to do this together. Okay, if I get something wrong, I'm sure you guys will let me know about it, okay? All right, here we go. First thing we gotta do, we always need to have a balanced equation. Okay, that is the most important thing, and that's where I would say a huge percentage of the mistakes come from, because it sort of infects everything else that you do. So let's walk through this. We can see that this looks like a combustion reaction. If you take a look up top, you're gonna notice the 5 different kinds of reactions, and this one looks like combustion. It is. So when this is combustion, we are going to change our products. It's going to go in, and we know it's always going to make CO2 and H2O. That part's the easy part. The part we got to get good at is making sure we balance this correctly. So if I go through the balancing process here, what I would normally do is say, well, there's 2 carbons on the left. That means I need 2 carbons on the right. Okay. I got 6 hydrogens on the left, which means I need 6 hydrogens on the right. And everything seems fine until we actually put in the total of oxygen on the product side. So if I add this up, remember I got to distribute, that's going to be 4 oxygens plus 3 oxygens. 4 plus 3 is 7. I got no whole number I can put here to make it 7. So our little trick around this was always, we basically make this a decimal. If I made that 3.5, and this is a 1, 3.5 times 2 gives me 7. So what I'm going to do is I'm going to double it. I'm going to double everything. So when I go do this, I'm going to have, this becomes a 2, this becomes a 7, this becomes a 4, and this becomes a 6. Okay, and the reason why this is important is we're going to be looking for a mole ratio. And remember, we have the entire reaction here. What we want to do is we want to read this carefully and narrow it down to 2 things. Okay, we're going to look at what we're starting with and what we're trying to predict and end with. Okay, so let's read that right now together. It says we're looking for the volume of water vapor, and we're starting with 50 grams of our fuel, which is ethane. So when I look up here, that means I'm dealing with ethane. Whoa, I didn't want that to happen. Let me see if I can get rid of that stuff. This is our ethane right here, and this is our water. Those are the 2 we're looking at. For these purposes right now, we don't care about the others. Okay, the others are there, we're just not going to analyze it. We want to know, starting with 50 grams of this, how much water is going to be produced. But remember, since we're dealing with gases, we don't really care the weight of water vapor. It's going to be so spread out and all over the place that it doesn't really matter how much it weighs. What we want to know is what size of container would it fill up at these conditions. So this is what makes gas stoichiometry a little bit different. So after you've got a balanced equation, and by the way, look over that really carefully, because sometimes if you forget a diatomic or you don't balance it correctly, everything is affected from that point on. Okay. So we got the balanced equation. Next up, we are going to do the actual stoichiometry part. And this is a little bit shorter than what you're used to with stoichiometry. We're going to start with 50 grams of ethane. So write that down. 50 grams C2H6. Always label what we're doing. Don't just put grams, put what it is. We used to do stoichiometry as a 3-step process. But when we're dealing with gases, we're only going to do 2 steps because it gets us to a spot that's actually more useful. Our first beginning step is always turning grams to moles. You guys know that? It seems like it's always a habit. So we're going to turn grams of C2H6 into moles. We want to know how many particles there are. Here comes the crucial spot. I am looking not for excess oxygen, I'm looking for water vapor. Okay. So I'm going to turn this last step into moles of H2O. So from the black to the red, I went from ethane to water. That's the key spot, okay? Now, let's do the mechanical stuff. These things should be habits that just kind of take over. Once we get our pathway set along the top, we're going to drag units down to cancel them. Grams, C2H6, just comes directly down diagonal without even thinking about it. Just do it. Over here, we drag our moles, C2H6. Everything in black represents ethane. Everything in red represents water. There's only one thing in red. Usually, we used to have a whole extra step on here. We don't have that anymore because we're not really concerned with how much the water weighs. We want to know what space it takes up. So we're going to stop right here. What I would like you to do is put this, equals N. This is our number of moles, and that's a key thing. Okay, now let's pay close attention to where some of these things come from. I'm going to try to color code this for you. Look up here at the blue numbers. Okay, we have 6 moles of water produced from 2 moles of ethane. It's a 6-to-2 ratio. So I'm going to put 6 moles of water are produced from 2 moles of ethane. Notice I'm matching 6 with the water, 2 with the ethane. So really look at those, that those are in the right spot. Now, that comes from balanced equation. So I'm going to put a BE right there for balanced equation. That's where that last step's going to come from. The step in the middle, this one comes from the periodic table. You guys have done this 100 times. The periodic table shows us 1 mole of everything on the planet. That will always be a 1 when you're dealing with the periodic table. 1 mole of ethane, well, you don't even need your periodic table here because you guys already know this. Carbon weighs 12 grams and there's 2 of those. Hydrogen weighs 1 gram and there's 6 of those. So you add all that up, that's 24 plus 6, we get a total of 30. Okay. So the green comes from the periodic table. The blue comes from the balanced equation. Always. And then we're going to stop right there. We're not doing the last step that we used to do. Now, let's take our calculator and get an amount here. Multiply the numbers on top, divide by the numbers on the bottom. So I'm doing this for the first time right along with you guys. 50 times 6 divided by 30 divided by 2. If I did this right, I got a nice number that's exactly 5, which usually isn't a nice whole number like that, but this time it happened to be, okay? 50 times 6 divided by 30 divided by 2. So I get a value of 5 moles of gas. And in this case, it's water vapor. That's the gas, okay? All right, we have done, recap. Phase 1 was the balanced equation, most important of all. Phase 2 was the actual stoichiometry, only a couple of steps to figure out what that reaction was going to produce. However, there's one more phase to this now because we have an amount of particles. We have 5 moles of water vapor particles. We need to know what space they would fill up, what kind of a tank they would occupy at these conditions. And the conditions really affect it a lot. So the way we do this with gases to finish it off is we are going to do our ideal gas law. PV equals nRT. And what you just found was N. So we have 5 moles. We know that one right there. Now what we got to be careful of is all of these units have got to be very specific in order for this to work. So let's take a look at what we have to work with conditions. we go up here and it looks like we've got 35 degrees Celsius. That's our actual temperature. So 35 degrees Celsius. You guys know we have to add 273 to that to turn it to Kelvin. So 35 plus 273 looks like it's 308. So there's our Kelvin temperature. That's the one we'll use. We know our constant is 0.0821. And it looks like our pressure was 0.86 atmospheres. Now, double check every problem you get that you have the right units. Atmospheres, moles, Kelvin. If you do, it means your final result in volume is going to end up in liters, and that's what we're looking for here. So let's set up what we have to work with. We've got our ideal gas law. PV equals nRT. Pressure times volume. My pressure is 0.86, so 0.86. I got a volume, but I don't know that. I got N is 5 moles. R is 0.0821, our ideal gas constant. Remember, that's the experimental value that makes all this work. And then T is 308. It's algebra time. I'm going to multiply these numbers together, and then I'm going to divide by 0.86 to get it over to the other side. So I'm going to take 0.86 and get it over here. It's going to end up on the bottom. So my volume is going to be all those multiplied on top divided by 0.86. Let's do that right now in the calculator. Make sure you're able to get this about the same thing I am, give or take for rounding. 5 times 0.0821 times 308 divided by 0.86. I get a value of 147.01, so I'm just going to round it off, around 147 liters of water vapor. That seems like a lot. 147 liters is a big amount. But let's remind ourselves of something. I will be right back. Okay? Over in the corner of the room, if you look to your right, up on the bookshelf, something that looks like this. This is our visual aid. Okay, remember, 22.4 liters is 1 mole. That's at STP, which is a pretty cold temperature. So if we raise this up to 35 degrees Celsius, and we drop the pressure, this is going to swell up even bigger. Well, I have to have 5 of those because there's 5 moles. So it's going to be 5 spaces bigger than this. 147 liters doesn't start to sound all that big. Okay, so this is kind of your way to reset and see if something seems normal to you. All right. Now, as you're working on some of your homework, I want you to try this stuff out. I'm not asking you to be perfect at it, but I'm asking you to make progress. You have homework that has a front side and a back side. If you don't have it because you were gone that day, come take a look at the front table and find one. Okay, what I expect out of you is that you try a couple of these out on your own. And if you don't get it right, you don't get it right. I want you to at least have something on paper so we can analyze it. So when I come back, I can figure out what I need to do to help you get to that spot. So if you take a look at this 3-phase situation, you got a balanced equation. 3 out of 4 mistakes will come from that spot. Okay? If you make it through that and get that correct, then we got some stoichiometry, but it's pretty straightforward. Like there isn't a whole lot of room to mess this up. This comes from the balanced equation. This comes from the periodic table. Every time it's going to look like that. Okay. And then the last part, PV equals nRT. This isn't all that undoable either. It just has some details you got to watch for. Make sure it's atmospheres, moles, Kelvin, and then rearrange it correct algebraically. So what I'd like you to do is try some of these out, see if you can get all the homework done, but really it's about quality, not quantity. Get something done and get it done right. And if it doesn't work out and you don't get about the answer that I did, look over your work and try to pinpoint which of those 3 phases might be going wrong. And if you can figure that out, then I can at least know what to do to help you out when I get back. Okay? All right. So take the rest of the time we got here, go to it, see if you can get some of this done. I would like you to stay where you're at, work independently, and force yourself to set this up on your own. And then if something's not working, check with someone nearby and see if you can pinpoint what might have went wrong. Don't use it as a chance to just get something on paper. Use it as a chance to really analyze your own work. All right. See you later, guys. Thank you.